That's my computer, retard.
He's had his computer for so long.
What? You're making another bag? Wait. Computer bag and Taylor's computer bag are very
Sorry, I just looked at the back. That's not an excuse.
Okay. What's the difference? The inside?
Yeah. Wait, you're already sharing?
For one thing.
I already started recording. So
Whatever you said, it's become a history now.
what's that?
I don't do
Really?
Wait, first did.
This is low resolution.
Okay. Today we are going to introduce a very useful topic.
This is called PID control. All right. So, okay. So in the last few lectures, we learn motors, we learn sensors, right? So in the homework, you guys learn how to control all kinds of motors, and you also learn how to read data from sensors. So how many sensors did you guys finish? Touch sensor, distance sensor. Elena, who finished distance sensor?
I thought it didn't work
Alright.
well. I don't know, there's something wrong with the motor. I don't know why.
Who finished the get position sensor? I'm you, gyro.
Use the gyro.
We use the IMU for the gyro.
Did you achieve the goal?
Yeah.
So what's the behavior?
Yeah, like the touch sensor, if you touch one sensor, and it hits the right sensor, it'll turn left.
Not exactly that.
Okay.
Well, that's because the wheel.
Okay.
Not the wheel.
So when you guys use the old Tyler, do you want to have a byte on the left as well? By the slider.
But no, that was because this was coming down like this.
Can you put it down? Put it down. Okay. Focus on the left. Yeah. So when you use the gyroscope to control a robot, what's the behavior of the robot? When you ask to turn 90 degrees, right? What happens?
It finishes and then it stutters. After you let go of the touch sensor, it stutters and then it turns 90 degrees.
Okay. When you use the gyroscope to turn, did you finish that?
Yeah.
So what's the behavior of the robot? Did the robot stop at exactly 90 degrees or the evolution?
No, well, okay, so
It started.
it finishes, stutters, and then continues to move forward. We made it to move forward, so it's supposed to move forward after it turns 90 degrees. So it turned 90 degrees, stutters, and then moves forward.
Does it move more than 90 degrees or less than 90 degrees?
I think a little bit more, right?
Yeah.
Because what you said when it stutters. So
Okay, this is exactly the reason we want to have move on to talk about the control. So whatever the state machine code you guys write now, it is say, for example, you want to move to one place. You write a code, put in the state machine, monitor how far you go, how many degrees you turn. When you reach your goal, say you move 3,000 steps, you immediately stop. But effectively, when a robot stops, you overshoot. When you turn, you overturn, right? But what if in a competition we need to stop at exactly 90 degrees? What should we do?
stop making a little less.
What? How do you know? Yeah, make a little less. That's one thing. Okay. What else you can do?
Turn it back.
So how do you turn back?
Code.
So you put in a state machine. Say in a state machine, but in a state machine, you just check once. When you achieve the goal, you immediately go to next state, which is stop state. So how do you double check again?
Don't go directly to stop.
Okay, you want how many times you want? So you want to check once more and say start. Is that good enough? Why? Then that's not efficient. You have to check whatever. If it doesn't stop, then what should you do? Say you find out it's overturned by 2 degrees. What can you do?
Give up.
So
Go back 1 degree. Yeah, it overshoots.
how much power is you going to put there?
And now, whatever the PID control set is.
Right now, didn't do any PID, right? So exactly, you will find out if you want to solve the exact. This is exactly the problem I'm trying to solve. You want to control something, stop precisely at somewhere. If you don't have this, all the state machine will go so far. It's called open loop control. Okay? Open loop control it is. You just go there. When you achieve, stop. You never double check whether you go there at all. Right? Another example is like you do robot dance. You just go say, hey, move to the left by 5 seconds, move to the right for 5 seconds, but how far you move, you don't know. Right? And you move by some distance, 3,000 steps. When you achieve 3,000 steps, you just stop. The robot will keep moving. Depends on your robot. Your robot is as light, or your robot is staying on a slope, or downhill or uphill. It could be. When you stop, your robot will just roll down the slope. Right? Now, how do you go there? So, but open loop, it's very simple, right? You sort of achieve your goal immediately. Everyone can write this simple code, right? But FTCs will require more elegant program, professional program, right? So we need to go to the second one. It's called closed loop, which means a feedback control. When you do something, you have a feedback. Take a look at, do I really go to the place, right? Right? And there's a little bit trick. For example, if you need to turn 90 degrees, right? When you are far away, you're probably going to apply big power to move that fast, right? But if you stop, you found out you overshoot by 2 degrees. You're going to apply big force to swing back? No. If you apply big force, you probably swing back by 10 degrees. And you check again, you apply the same number of force. You never go to the 90 degrees. Is that right? So what can we do? It is you have to make your power feedback proportional to the arrow, the distance. The arrow means your current position minus the target distance. Right? That means your power, your feedback power, is proportional to the distance to the arrow you run into. Is that right? So this is the first thing we call P. PID control, P. Got it? Proportional to the arrow you run into. Got it? It's very straightforward, right? So if you have a proportional control, you have really nice control. That means if you're a couple degrees off, you just apply a little bit force, you are there. Right? If you have a further wing or section, I will explain later, okay? Alright. Okay. So this proportional control is a typical feedback control, right? There's another kind of control called feed-forward control. What's the feed-forward control? You just mentioned you expect your robot will overshoot, right? Then what should you do? You just underturn a little bit, right? But the problem is how much underturn you're going to do. It depends on the friction of the robot and the speed of the robot. You don't know the value. You cannot calculate the value. Then what should you do? What should we do? Huh? Okay, we still can do it. There's a one term in PID control D. D means derivative. Basically, look at the trend, right? So suppose you want to move 90 degrees, right? In the beginning, you apply huge power, so robot swing really fast. And when robot find out you apply big force, the gap, the arrow decrease really fast. Then what robot should do? You should automatically slow down and disobey the proportional command. For example, if you do proportional totally, that means say your 90 degree you map to 1.0 power, full power 1.0. Your 45 degree will map into half throttle, 0.5 degree, right? Right? So that means when you're turning at 45 degree, you're still accelerating, right? So that means 45 degrees is still overshoot. So if you have a second turn, look at the derivative of your speed change. So you find out your arrow reduce really, really fast. It's not constantly reduce really fast. That means you should slow down, right? So that means when you turn at a 45 degree point, you should not use full power. Okay? Or you should not use 0.5 at all. You should reduce more. Basically, you need to break it. Or sometimes you need to apply negative force to break it. Right? Does that make sense? So this is another thing called D comes from derivative. Because you look at your trending, look at the trending, how the arrows turns to be. Right? Then you can do, based on the trending, you apply additional control. This is called feed-forward control. Is that right? Understand now? Okay. Then you will wonder why the integral. Why we need to do integral? Integral, it is you're going to add up the arrow, then apply proportional feedback force to the add up accumulative arrows. Why is it useful? One useful case it is when you go up hills, right? Say for example, you want to move by 2 millimeters up hills. Based on your proportional, 2 millimeters, you're probably going to apply 0.00 something power, right? If we apply not much power, what will happen? The robot will roll back, right? Right? How do you solve this problem? So basically, the integral it is going to add up the last n seconds error. So for example, you check your distance 10 times per second. You find out the last few seconds your distance, arrow distance increase instead of decrease. Then if you add those arrow up, basically sum them up. Say for example, in last 1 second, every second you find out your gap instead of 2 millimeters, your gap turns to 3 millimeters, 4 millimeters, 7 millimeters. All that adds up into like a 15 millimeters, right? Basically longer the time you reach your target, you're going to apply much bigger force because your cumulative error is bigger. So this can solve the problem when you go up here. The proportional of your feedback power is not big enough to compensate the friction or external force. So you're going to apply this historical error to speed it up, right? There's another example like your coach training your like a swimming. You go to a swimming team. Your coach make your say coaching plan. Say within 2 months, your 100 meters. What's your 100 meters?
1 minute 30.
Okay. 1 minute.
It says 1 minute 3.
1 minute 3. So suppose you're 1 minute 30th to begin with. You say my target is I need to reach 100 meters in 1 minute and 5. You're going to improve 1 minute 50. What's the 1 minute 30 seconds to 1 minute 5 seconds, right? When the coach see that, the coach make your plan. Say in order to achieve this, he's saying because you have 25-second gap, he expects you to come to the swimming pool training twice a week in order to reach your goal, right? This is proportional to, right? And after 3 months, you find out, hey, you have 20 seconds. You only improved by 2 seconds in 3 months. So what can you do? No, you say, oh, twice a week is not good enough. Let's do 4 times a day, right? Right?
An hour.
Right? This is integral because he, based on the 3 months history, he found out that's not enough, right?
But why did you wait 3 months?
Because you need time to observe.
2 months.
The thing is, you need time to observe. For example, if your observation time is very short, your feedback won't be not reliable because you're too sensitive.
The goal is 2 months, so like I think he's like, hold up, I have a 129.
Okay, but basically you guys understand the idea, right? For each P, I, and D serve its own purpose. P, proportional is basic control, basic feedback control, right? I is like very important control based on whatever the change, okay? To handle like you've got a higher resistance, something like that. D, it is make sure you slow down, or even catch up even faster, right? Right. For example, another thing we compensate this problem is even for the training, if you go up hills, instead of decrease the arrow, you increase the arrow because you roll back. The trending is totally different. That means both the integral and the derivative, the training, will ask you to go apply more power, right? Right? So basically PID control is these 3 terms. Look at your current condition, proportional. Look at your history, that's integral. Look at the future, that's derivative. This is basically like your life, right? You not only look at your current status, you also look at the history, look at the future. That's fundamental control for everywhere, okay? All right, now how do we implement the PID in a code? It's straightforward. You first find out what's your error. Basically, you have a target value. If it's travel by distance, then the arrow, it is how far you travel and what's your target. Then the delta is the arrow. If you make a turn, then the number of degree you turn is the arrow. You miss is the arrow, right? Then if you want to say implement the rope the dance, say you want to move position A to position B. Now, every time you get the position, and you keep calculate, use the geometry to calculate the distance between your position and the target position. How do we calculate it? It's by x squared plus y squared and square root of it, right? What's the distance of in x? And what's the distance in y? Then you apply the square root of the sum of the square in each dimension, right? This is totally typical geometry, right? Understand? All right. So, and when you calculate this, and you just simply use a constant value, multiple to the arrow. Basically you have a value times the arrow, the proportional arrow, or your historical arrow, your trending arrow. Got it? So, and to implement PID control, it's straightforward. you need three values, 3K, right? KP, KI, and KD, right? And how do you calculate the feedback control? Let's look at the code, okay? Is that simple? You calculate your current arrow, you use KP times KE. That's the basic feedback power, right? Then you plus KI times your integral arrow. Got a second term, right? Then plus KD times your trending arrow, right? Got it? Then when you, based on this, you return, the return could be a feedback power, or could be anything control vectors. The robot can be controlled by power. It also can either controlled by the voltage or controlled by current. But in the motor, it's controlled by how frequent you send out full power. Okay? When you apply the motor, did you guys hear an sound in the motor? Did you guys hear it? When you drive the motor, drive the robot, you heard the sound, right? Right? Do you guys know how it works? Basically, the robot sends the pulse to the motor. If you apply full power, the robot will basically send out full power 100% of the time. If you want to apply half of the power, then the motor will alternate power. Say 50% of the time you will send power by some seconds, then drop to 0. Then send another power. Basically, 0.5% of the time you send power, 0.5% no power. This is how the robot controls it. Got it? They are not controlled by voltage. They can control by how frequent they send out the power. Got it? Okay. So, okay. Then at here, you can see for each K, you have another arrow, frequency arrow, integral arrow, and derivative, trending arrow, right? The ultimate function basically just turned up, right? Right? Okay. You have to remember this function, okay? Got it? Okay. You may curious why we need the maximal integral arrow. Why we need that? Why we need that arrow? This arrow is used to control the long-term memory and the short-term memory, right? For example, when the car want to go up slope, right? If it's stuck there for a long time, then the integral arrow adds up to be huge, right? It will be a humongous number, because suppose in 1 second, you calculate the arrow 10 times, right? If it's stuck there for 2 seconds, you probably just you have the 20 times whatever the error, right? If it's stuck there for 1 minute, for some reason, right? So as a result, your cumulative error will be really huge, right? If the cumulative error is huge, when you want actually correct yourself, say you already move up hills, your error decrease. You will overshoot a lot to break things even, to make the integral error to be 0. Is that right? In order to make the integral error to be 0, then you have to go up slope a lot. You have to overshoot a lot, right? Then come back. Is that a waste of the time? Right? So this is why sometimes people have to learn to forget something. Otherwise, your life is miserable. For example, you have some people always be mean to you. So you say, oh, that guy is mean. But suppose that guy change, right? Oh, I'll just give you one example, right? When some people already change, say, if that guy be bad to you for 3 years, right? But that guy, all of a sudden, that guy changed. He turned to be a good person. It took another 3 years for you to think he's a good person? Yes or no? No. Possibly? right? So basically, this just give you one example. We need a cap to the his historical error. When a historical error is big enough, is enough. Because if you know some people is bad guy, you observe him for like 3 months, you know he's bad guy. Observe him for 6 months, he's a bad guy. It's just, you don't need to keep observing anymore because you know he's bad guy, right? Right? So probably 1 month is good enough. You don't observe anymore, or you just observe less, right? So basically, this is just in order to prevent you to overreacting to his badness, right? Because he's a bad guy. For example, some people is bad, is really mean. So if he's been mean to be 3 months, you just don't like him, right? If he's been bad for 6 months, you're going to kill him.
Okay.
If he's been bad for 12 months, you're going to smash him into pieces.
Which one is marginally worse?
So, right? So basically, this integral cap is basically saying your reaction, once your reaction is good enough, is enough. Don't overreact. Got it? Got it?
No, that's 1 year.
Yeah, but
It was already 12 months.
In 2 years, they'll move to conflict.
if he's already
Yeah.
bad, then he can't be bad anymore.
Yeah, they give you another example. When,
Right.
say if you're,
Just kill them.
for example, your robot, hey, listen.
That's 2 days.
Listen. For example, when a robot is stuck on a slope, okay? It's stuck slope for 1 minute. That means you are going to overshoot 1 minute to compensate the error. How dumb it is, right? If the robot is stuck in the rope slope for 1 minute, you just need to say 10 seconds is good enough. You probably just memorize 10 seconds. I already know it's stuck, right? You don't need to memorize the 10 seconds, 1 minute, right? Basically, the key thing is prevent you to overreact to the accumulated error and be stubborn. Means somebody say if you like you're stuck on the slope for 1 minute, you're going to overshoot for 1 minute to compensate it. You're not going to do it, right? Got it? Got it? So basically, that's a very simple trick to prevent your robot overreact to some errors. Got it? Got it? So that means I think today we run out of time. So in next week, we're going to teach you how to tweak this error, tweak this parameter. Basically, how do you find out the sweet spot for these K values? Got it? If those values are not right, your robot will behave crazy. All right? Okay? That's, for example, if the proportional value is too big, then when you are off by 2 degrees, you put a huge feeding power. So your robot is crazy, right? Proportional, right? If your feedback power is too big, you're off by 2 degrees, then you will overreact. You always overshoot. You never go to the good place, right? Got it? Okay. If you apply tiny force to the something, then you'll be really slow. It's like a dumb people. You totally count down the integral error.
Good for you being mean.
What? I mean,
I feel targeted.
North.
okay. So it's really tricky to turn this value. Okay. In next class, we're going to help you basically teach you how to tweak it manually, PID values controls manually, and how to write a program to tweak it. You don't want to tweak it by hand, right?
Of course you do. That's just like bashing in math. I do that all the time.
Okay. First, we teach you how to tweak it manually. You know how to tweak it. Once you understand it, let's write a program to tweak it. Okay? Got it? So, and different robots, they need different values. Okay? So basically, we need to, that's another learning curve you guys need to overcome in the next few weeks. Because in order to do the robot dance elegant, you need PID control. Otherwise, the robot will be crazy. You say move by 3 feet. When robot dance on the stage, you overshoot the affair of the stage.
Okay.
Right? Or when two robots do like a group dance, your robot will crash into each other. Crash to each other, right? Right? Or if your parameter is not right, then your robot will be acceleration really slow. When some robot already finished like a routine 2, the first robot still work on routine 1. Right? Everything will out of sync. Is that right? Okay, basically how well you guys control the robot to do group dance. Group dance. We need to control 3 robots and 3.
Four.
Either way.
Do we have 4 groups?
Yeah, you have 3 robots.
Yeah, us 3, Helena, and Jake,
Yeah.
Tyler, me, and
Yeah.
Caitlin, and him.
Derek.
Yeah. So just use 3 robots. Don't worry. Just use 3 robots to do group dance. How well those robots coordinate each other is totally comes on how well you guys do PID control. Okay? Got it? Okay.
We have
So this is okay. This is today's class. Okay.
It's really broken.
It's like one metal